45.0 milliliters of a 0.250 molar calcium chloride solution is treated with excess 1.00 molar silver nitrate solution. What mass of precipitate will be produced, assuming a 100% yield? So the problem tells us that we have calcium chloride reacting with silver nitrate, and we want to find the precipitate formed, the mass of precipitate formed. So what we'll do here is whenever we're dealing with these ionic compounds in solution, they will react via double displacement reaction. So what we want to do here is write products where we simply just swap the ions. So for example, instead of calcium chloride, we'll write calcium nitrate, the cation and the anion. So the formula for calcium nitrate is CaNO3 2. And if we follow the solubility rules, the nitrate salts are going to be soluble in solution. So we'll write AQ for soluble. And our other product will be silver and chloride. So here, the formula for silver chloride is simply AgCl. And according to the solubility rules, chlorides are soluble in solution except, and one of those exceptions is silver. So we'll write S for solid. So this is our precipitate. Our problem also tells us that we have 45.0 milliliters of our calcium chloride, and the molarity is 0.250 molar. We have a 1 molar solution of the silver nitrate, but we also are told that this is an excess. That means that our calcium chloride is the limiting reactant. We need to balance the equation next. And we'll balance by inspection. I have other videos where we practice writing the formula equation and balancing the equation. So here I'll balance by inspection. There's 2 nitrates here, so I'll put a 2 here. And then we can balance the silver chloride with a coefficient of 2. And now everything is balanced. Okay. We're doing stoichiometry, so we want to take advantage of these mole-to-mole ratios to find the amount of precipitate formed. So I need to find the number of moles present. I'm dealing with solutions, so I need to convert these volumes, or this one volume, into moles. So I'll convert the milliliters to liters first. I'll cancel the milliliters. And the reason I do this is because I can now convert the volume of liters into mole of the calcium chloride. And notice I can cancel liters, and if you look closely, this ratio here of mole per liter is the molarity. And that's given to us in the problem. 0.250 mole of the calcium chloride per liter. So far, our milliliters and liters have canceled. I have now successfully converted to the mole of the calcium chloride. So what I can do now is convert to my precipitate, my product. So we'll convert to the mole of the silver chloride and cancel mole of the calcium chloride. These mole-to-mole ratios always come from the balanced equation. So according to the balanced equation, 1 mole of the calcium chloride will yield 2 moles of the silver chloride. And since we're looking for the mass, the last thing we'll do, of course, is just convert to the mass of the silver chloride and cancel the mole of the silver chloride. This, of course, is the molar mass. We can go to the periodic table and find the molar mass. For silver chloride, this should be 143.32. grams per mole. And this is what we want to see. I'm sure your instructors will appreciate this, showing all the units canceling. I know I do when my students show me the units canceling. And when we run this calculation, at least to 3 significant figures, that's what we start with here, all 3 significant figures. Our answer is 3.22 grams of the silver chloride is produced. 12.0 milliliters of a 0.200 molar sodium carbonate solution is mixed with 7.00 milliliters of a 0.500 molar magnesium nitrate solution. What mass of magnesium carbonate is produced, assuming a 100% yield? In this problem, we have sodium carbonate, and this is aqueous, reacting with magnesium nitrate. This is also aqueous. For these ionic compounds in solution, we'll write products using this double displacement reaction. So one product would be the sodium and the nitrate. The formula for sodium nitrate is NaNO3, and so by solubility rules, nitrates are aqueous, alkali metal ion salts are typically aqueous, so we'll write aqueous there. And our other product would be the magnesium and the carbonate. So the formula for magnesium carbonate is MgCO3. According to the solubility rules, carbonates are typically precipitates or solids in solution. So we'll write an S for solid. The reason the carbonate is aqueous here is because it forms a compound with sodium, and the sodiums are typically aqueous. Okay. So next we'll balance the equation. This one's pretty simple to balance. 2 nitrates and 2 sodiums on the reactant side, so we can balance the sodium nitrate with a coefficient of 2 here. So we want to know how much precipitate is formed. What is the mass produced, assuming a 100% yield? Notice that unlike our previous example, no excess reactant is given to us. There's a finite amount of reactant. And so what we need to do here is find the limiting reactant. There's a couple methods to find limiting reactant. What I'll do here is a method where we're just going to find how much precipitate can be formed if sodium carbonate is limiting. And then we'll run another test where we find how much precipitate is formed if magnesium nitrate is the limiting reactant. Whichever produces the fewest is the limiting reactant, because of course the limiting reactant will limit how much product we can get. So let's do a test with the sodium carbonate. I'll take my 12 milliliters of sodium carbonate and we'll convert to liters. And then I'll convert to mole. And cancel liters. Mole per liter, this is the same thing as a molarity. And now that we have moles, we can convert to moles of the product. So in this case, it's a simple 1-to-1 ratio. For every 1 mole of the sodium carbonate that reacts, there's 1 mole of the magnesium carbonate produced. And I'll go ahead and convert to the mass at this point. You can find the limiting reactant by converting to moles, but in this case, the question's asking us for the mass, so I'll go ahead and convert now. And we'll use our answers to compare here in a moment. Grams per mole, this is a molar mass. And so this shows us our units canceling here. Looks really nice. And so we end up with the grams of the magnesium carbonate. And when we run this calculation right here, we get a mass of 0.202 grams of magnesium carbonate. So let's pause there and just discuss. This is the mass that can be produced if our sodium carbonate is the limiting reactant, but we don't know that yet. What we would need to do is now test the magnesium nitrate. And so let's go find out how much magnesium carbonate can be produced from the magnesium nitrate. So very similar, I'll take my 7 milliliters of the magnesium nitrate solution, convert to liters, then convert to moles using the molarity. And then convert to my product. And just like I did up here, I'll go ahead and convert to the mass. So notice this last step will be the same. Okay, I'm running out of space here, but this is the conversion to the mass of the magnesium carbonate. And when I run this calculation, I get a mass of 0.295 grams of the magnesium carbonate. So what does this mean? There's two answers here. Remember, when the sodium carbonate reacts with the magnesium nitrate, the magnesium carbonate will be produced. Notice that the sodium carbonate can only yield 0.202 grams of magnesium carbonate. Once this is produced, the sodium carbonate is now finished, or at least the carbonate is now gone. And so notice that the smallest amount is all that we can get. There's not enough carbonate to give us any more. The sodium carbonate will be limiting. The magnesium nitrate is in excess. And our magnesium carbonate produced is 0.202 grams. Toxic ions like chromium 3+ are treated with sodium hydroxide to precipitate out the chromium. What volume of a 1.00 molar sodium hydroxide solution is required to treat 35.0 milliliters of a 0.800 molar chromium 3 nitrate solution? Here's a really interesting water treatment problem. Some of these toxic ions like chromium can be precipitated out, and of course you can filter out those precipitates and clean the water. In this case, we'll say we have a chromium nitrate solution, and we can precipitate the chromium ions with the sodium hydroxide. So as we've done before, we'll have a double displacement reaction. We'll write a product of chromium 3 hydroxide. Chromium 3 hydroxide has a formula of CrOH3. Hydroxides typically form precipitates due to the solubility rules. So we'll write an S for solid. And our other product would be the sodium nitrate. Sodiums and nitrates are typically soluble. So we'll write a Q for sodium nitrate. And we can balance the equation. 3 nitrates, put a 3 here. We have 3 sodiums and 3 hydroxides, so we'll have a coefficient of 3 in front of the sodium hydroxide. So the problem says we have this hypothetical 35 milliliter chromium nitrate solution. We'll say the concentration is 0.800 molar. And we have, let's say, a 1.00 molar stock solution of sodium hydroxide, and we want to know what's the volume? How much volume do we need to react? So this is a stoichiometry problem where we're comparing the reactants. How much reactant do we need to react with another reactant? Notice we're not asking about the precipitate like we've done in our previous examples. We're just comparing reactants, but it's still stoichiometry. So what we want to do here is convert to the moles of the chromium nitrate and then use the stoichiometry, the mole-to-mole ratios, to convert to the sodium hydroxide. So we'll do that right here. We'll start with our 35 milliliters and we'll convert to liters like we've done. And we convert to liters because in our next step here, we're going to convert to the mole of the chromium nitrate, chromium 3 nitrate. And of course, mole per liter, this is a molarity. Now that we have our moles of the chromium nitrate, we can convert to the mole of the sodium hydroxide. And so this is our stoichiometric step. This is where we use the mole-to-mole ratios from the balanced equation. So according to the balanced equation, for every 1 mole of the chromium nitrate that reacts, there are 3 moles of the sodium hydroxide that reacts. So now these units cancel. And I'm running out of space here, so I'll continue below. We have moles of the sodium hydroxide. Now notice what I'm going to do here. The question is asking what's the volume of the sodium hydroxide. So from mole of sodium hydroxide, I can convert to the liter of sodium hydroxide and cancel the mole. This relationship of moles and liters is the molarity. Now, it looks a little bit different than this ratio right here. Of course, we're canceling moles, so this goes in the denominator. But the representation is the same thing. This is the molarity. So 1.00 m represents 1.00 mole of sodium hydroxide for every 1 liter. And so notice how the mole of the sodium hydroxide cancels. So now I've done it. I found the volume required. Now, in most general chemistry courses, we're dealing with small amounts, usually on the milliliter scale. So it's pretty common that we'll convert to milliliters. And so this ratio is 1,000 milliliters in a liter. And so we've done it. When we run this calculation, we'll get 84.0 milliliters of the 1.00 molar NaOH solution. This is the amount required to precipitate all of the chromium ions from solution.